Hi guys, welcome to the channel Code by Raghav, and in this video we are going to solve the lead code question number 540, that is single element in a sorted array. It's a medium type question and it has been asked in many interviews, and you can see Amazon, Apple, Microsoft, Google, Atlassian, Nvidia, Meta, Goldman Sachs. So big companies have asked this question. So let's read the statement what this question says, and we already know this is the part of our binary search playlist, but in the interviews you have to find out which approach is best to solve the question. So you have to find out the clues that fits the approaches. So let's read the statement and try to solve it. It's a very interesting question and it changes our binary search default template a little. So let's see. So we have given an sorted arrays. There's the first clue. So we have to use. So we might use the binary search approach. So let's confirm consisting of only integers where every element appears exactly twice. Okay. So in the sorted array, every element appears twice except for one element, only one element which will appear exactly once, and rest of the element appear twice. So return the single element that appears only once. Okay. Your solution must run in O of log n. That's the second clue. We have to use the binary search and in O of one space. So we have to do the operations in place. And if you look at the example, so there's only one element, that is 2. It appears only one time and rest of the element are appears twice. So that's why the answer is output is 2. So the approach is very simple. Let's say you have an array and you are standing at this point, wherever you are standing. Let's say this point, this is your ith index, and let's say this is your 1, and let's say 1, 2, 2, 3. So where you are standing, wherever you are standing, so you check if the next element is similar to this ith element. Yes, it is similar to the ith element. Then we check what's the length of the array of the rest element. So what, so what's the length? It is 3. So the length is 3 means it is an odd length. So the possibility of the single element will present on this half, or this, on this length, on this part of the array is 100%, because it will always present, because in the question we have already one element that it will appear only one time. So the length is 3, so it is an odd number, so you can fit only one single element. And if the length is 4, let's say there is 3, so length will become 4. So there's can be no single element because they are already in pairs. If they are single means 3 is single, and let's say you just write another element like 4. So the question changes. Now there is two single element, but in the question there can be only one single element. So if the length of the part of the array is odd, means single element is there. If it is even, no single element. This condition is for when the ith element is equal to the next I plus 1 element. There will be case, let's say this is your 1, 2, 2, 3, and you are standing here. Let's say 1 is right here. You are standing on this ith element, that is 0, 1, 2, 3, 4. Now you check, is it equal to the I plus 1 at element? No, it is 2, it's different. So then you again check if the length of the rest of the part of the subarray from this ith point, is it even or odd? It is odd, it is length 3. So the single element will be on this side. There so it is 3 means the single element will be on this part of this subarray. If it is odd, let's say add 3, and now the length is 4, that is even. So this, in this part there can't be the single element, so it has to be on the left side of the subarray. So, and there is no example that it will be not there, single element will be always there. So the, if you say, if you delete this, so the single element is 1. Now let's try to dry run, and here are some changes in the binary search template, because it's easy. Instead of doing the linearly iteratively checking, we just simply take a mid and eliminate the search space by half and do it for the rest of the iterations. So let's copy the array example. Now let's try run how we can implement the binary search into this. First, let's simply apply the normal binary search template. So we take a, first we write the indexing. Let me write it: 3, 4, 5, 6, 7, 8, and the output is 2. So we initialize the low from 0, high this n minus 1, that is 8. Now we run, the left is, that is our default condition. Now we find the mid. So what is mid? I'm taking the normal simple formula because the, now 8 minus 0 by 2, so the mid will become 4. So this is our midpoint. Now we ask, now we take a boolean is even, because we have to calculate of this based on this based is even. So how we can calculate this length of this part of length? By just simply saying if h minus mid difference, if h or mid difference modulo by 2 is 0 by 2, means because the element is appearing twice, appears twice, so that's why we are dividing by 2. So what's the h? H is here 8, mid is 4, so 4 modulo by 2 is 0, so we set is even true, else is even false. Now we write our default condition is nums of mid is equal to the nums of Mid plus 1. Is nums of mid is equal to the mid plus 1? No, it is not. So we go on the else case. Let's leave it here. Go to the else case where nums of mid is not equal to the nums of mid plus 1. So, and now we ask in this else condition, if is even, is the rest part of the subarray is even? Yes, it is even. So there cannot be this. So the single element will not appear on this part of the subarray. So we have to move this h if it is even. So how will you move this h high? In the default our binary search, we eliminate this search space, this part of the search space, by simply doing h is equal to mid minus 1, right? But in this question the mid element can also be the single element. As you can see, the mid element can also be the single element. So instead of doing the mid minus 1, we will simply do mid plus 1. So h is equal to mid. Else, if it is not mid, means if the it is not is even, means the part of this subarray is, the length of this subarray is 3, means it is odd, means the single element will be on this side. We remove this search space, this, eliminate this search space, we will move, update our low. So low will be mid plus 1, low equal to mid plus 1. And now let's again calculate. So our h is come here on 3. Now the mid will become 4 minus 0, that is 2. Our mid will come here. Is nums of mid is equal to the nums of mid plus 1? No, it is not. So we have to calculate the part of this subarray. Now our search, this search space is eliminated. We no longer need this. So we will calculate the length of the subarray and see if it is even or not. So h minus mid, 4 minus 2, that is 2, and 2 modulo by 2 is equal to the 0. So the length of this subarray is even, means there cannot be the single element present in this part of the subarray. So we have to eliminate this also. Now h will come here to the mid. Now we ask, now we calculate the mid again. 2 minus 0, that is 1. So mid will come here. Now we again calculate the, is this is even? No, it is not, because the 2 minus 1, 1 modulo 2 is not equal to the 0. So is even is false. So if the is even is false, what we will do means it is odd. So the single element will be present on this side of this, on this part. So we will move the L to mid plus 1. So L will come here. Now if you carefully look, currently L and H is on the same, pointing to the same index, and our default condition is L is less than equal to the H, means we have to again run the binary search. If you run, so the what will appear, 2 plus 2 4, so mid will become 2, correct? And if you do 2 modulo by 2 means h minus mid, so 2 minus 2, so it will always say is even is true, so we will end up in a loop, so it will infinite loop, so we have to remove this equal to sign. If you do not, if you apply this equal to sign, so it will give the time limit exceed error. And now our this condition is left. Let's see the second example. Let's try run this. It will also an interesting one. So 0 1 2, let me write the indexing. Low will point this, high will point this. Run the loop, L is less than H. We have already seen it in the previous example. We will calculate the mid. Mid will become 3. Mid will become 3. And we will calculate is 3. There is our mid. It is again not equal to. Let's see. Is even H minus mid. 6 minus 3. 3 modulo is not even, means is even is false for this subarray, for this part, means the single element will present on this side. So what we will do, we will update our low, so our low will come here on the mid plus 1. Now we again calculate the mid. 6 minus 4. Let's again calculate the mid. Lowest 4. 6 minus 4, 2 by 2, so this will become 5. So our mid will point this. Is nums of mid is equal to the nums of mid plus 1? Yes, it is. Now we have got the situation. First let's calculate the is even. H minus mid 1 modulo by 2 is still false, but now we have got nums of mid is equal to the nums of mid plus 1. Now what we write in this situation, if it is even, in this case it is not even. Let me take an example. Let's say this is your mid, this is your mid I and 2 2 3. So this is your mid is, so nums of I plus 1, it is equal. So what you will do, now you can see is even is true, means the part of this subarray is true. 4 length modulo by 2 is even. Yes, it is even. So what will you do, it is equal. So if you remove this part, what you will get, this 3. 3 is an odd length, means the single element will be on this part. So how will you update your low pointer? So you will update your low pointer by saying low mid plus 2, because we are moving 2 step ahead, because mid is there, this is our mid plus 1, this is also the same as the previous mid value. So we will directly update our low to this 2. And if it is not, let's say remove this 3, if it is odd. This is the conditions for if nums of mid is equal to the nums of mid plus 1. So 3 means it is odd. So as you can see, this forms a pair, this forms a pair, no element left. So for the odd, you directly update your h to mid minus 1. So there's no point of searching on this search space, so you have to eliminate this. So let's back to our example. Now we got nums of mid equal to the mid plus 1, but it is odd. As you know, this forms an pair, so no need of searching. So we will move our h to mid minus 1, h come here, condition is this. So you either return low, nums of low, or nums of high, everything is same at the end. So let's quickly write the approach and let's see. So int low equal to 0, high nums dot size minus 1. We will take a bool is even. We'll run a loop while low is less than high. We are not adding equal to, because if you add equal to, you will stuck in a loop forever. So it will calculate the is even true every time. Now we have to calculate the mid. Low plus high minus low by 2. Now we have to calculate the length of the subarray for the rest after the mid. Is it even or not? So let's say if high minus mid modulo 2 is equal to the 0, is even is true, else is even is false. Now we write our conditions. If nums of mid is equal to the nums of mid plus 1. Now we check if is even length, means this is your mid, this is your equal to the 4. So let's say this is your mid, this is equal to, now this is odd, so that's not the correct example. We have already seen it. If it is even, so means your mid and mid plus 1 forms another pair, so it will become odd. So for the odd, so this even, the length after removing this mid plus element, so it will become the odd length subarray. In the odd length subarray we have already know, so there will be a single element, so we will update our low, so we have to find the single element on that search space. So we have to eliminate the left half of this array, so our low will update mid plus 2, else high equal to mid minus 1. Now for this if else, nums of mid is not equal to the nums of mid plus 1. If is even, means on the right side everyone is in pair, no single element there. So but the mid can be a single element, so we will update our high to mid, else low equal to mid plus 1. And after all this, return nums of low or nums of high, both are same. Let's try to run it. It is accepted. Let's try to submit it, and it is accepted. We have used the log O of log n approach time complexity. We haven't used any extra space, so the space complexity will be O of 1. Thank you for watching. Make sure to like, share and subscribe.